You bet. Well, thank you, Randy, and I do appreciate the opportunity to present this morning. Few may have already seen this talk a few times. I've presented at the 2019 High Plains Conference, and back in March, I did a talk on this for the WFO Norman mesoanalysis discussion. So, if you've already seen this, material will be fairly similar. But excited to present this, mostly because this past severe convective season, we had an absolute dud out in southwest and south central Kansas for tornadoes. So it's probably still our biggest event in the last 2 years. But anyway, so there's a significant amount to learn from this case because while overall warning performance and associated services from the Dodge City office were good, we did have some minor warning placement issues that existed during the initial onset of the prolific tornadic phase of this main long-lived supercell. And that kind of gives a hint that there's still some areas needing improvement. And it really should be able to benefit all of our offices, whether you're within Tornado Alley, et cetera, or outside, there's going to be cases where can really benefit you. So the ultimate goal here is to look at some of the key training items brought forward by the Central Region TWIP to see if applying these modern interrogation principles would have helped in anticipating tornadogenesis in the correct location. Let's advance. Okay, so for this case, for those that are unaware, multiple rounds of convection that developed finally during the evening, but it's mainly this long-lived supercell that I've got highlighted here that was the main story. And it was a prolific tornado producer from essentially mid-evening to almost midnight before the convection kind of migrated eastward and became elevated. Several tornadoes along this phase, or along the supercell, but it's really this set here that began this period of really cyclic tornadogenesis and especially the onset of this where warning placement may have been issued that we're going to talk about today. So specifically about this tornado, and it's 3 counties, Meade, Clark, Ford counties. Obviously, nobody has to memorize where those counties are, but we had peak EF3 intensity on this tornado, although it could have been higher, and sadly, we'll never know for sure with limited DIs in some spots across the Great Plains. But fairly impressive path length of duration here. You see 26 miles in 45 minutes. So this was a fairly impressive tornadic event, but especially this tornado for being, existing for 45 minutes in that 26-mile path. That's impressive. Did kind of show you there in a map, supercell had already produced a brief tornado near the Kansas-Oklahoma border around 0039, but really nothing after that until the start of this Mineola tornado. And then that began this period, lasted 3 hours of intermittent and at times nearly continuous tornado reports. Tracks ending with one last brief tornado south of Great Bend around 0430. Not really digging into this, but I've gotten this question, so I added it into this set of slides that likely a mode change there around 0440. So whether it's increasing inhibition, associated migration, elevated convection, not sure, but more than likely that's why it stopped taking on supercell attributes and producing tornadoes. So very picturesque tornado. Started off more of a stovepipe looking thing, but because it existed for 45 minutes, it got progressively bigger and more intense. Interesting, went right through a wind farm. You'd think, oh, maybe this is going to cause some damage to the wind turbines, but we're not aware that it actually did any damage to the turbines, which is kind of fascinating. But unfortunately, this home here, where we got most of the EF3 damage, you can see the house was pretty well destroyed. A lot of walls were knocked down, and even this metal building, you can see, especially the beams were twisted. Interesting enough, some of the other buildings or farm facility stuff there in the background was less impacted. We think that the vortex tracked such that the left side of the vortex hit those buildings, because we saw more damage on the east side as this moved east-northeast. So may have been why those survived. I don't know, not a structural engineer, but nonetheless, a lot of damage. This is an interesting picture we also took here. If you needed some lumber, you could get some that day, but you might have to pull this out with a little more might, because this we believe it came off the house itself and swung around and was embedded in the ground, probably at least a foot. There's another piece there that somebody didn't know was there and unfortunately ran over. I don't know if their tire got taken out, but obviously something you see frequently with tornado surveys, but we tried to pull that out of the ground. We could not. So obviously definitely some intense speeds on this. So before I dig into the case, just want to highlight a couple things that areas that we talk about either in the TWIP training or have not highlighted specifically. And so one of the things we mentioned within the TWIP training is the utilization of what's called the KDP to ZD-arc separation vector in combination with the storm motion to get a qualitative estimate of the storm scale SRH. You can see here the example there, you got the photograph. So it's a very valuable tool. What we didn't mention is that the maximized prognostic capability of the separation vector angle is seen in more weak to modest low-level SRH environments. So obviously you may have enough deeper layer shear for supercells, but maybe the low levels, it's not quite there yet. So in those cases, the storm is having to generate most of the necessary streamwise vorticity to intensify the low-level meso. So that's where it really becomes beneficial. What we didn't talk about too is that in the opposite sense, in a high level SRH environment, such as on outbreak days, or maybe it's in the evening after the low-level jet forms, simply the existence of a ZD arc that's not disrupted, it's fully there, there's no hail cutting through it, that's likely enough evidence to support the development intensification level meso. And the reason being is that due to the higher ambient SRH, the storm in that setup is only having to nudge the total vorticity upwards to generate enough SRH to intensify the level meso. So in that case, a low separation vector angle may not be a problem because the storm is just nudging. So again, calculation of the separation vector angle kind of becomes optional in those environments. I would not discourage people from looking at it, but when you got 300-400 SRH in the lowest kilometer or 500 meters, if you just see a non-disrupted arc, that may be good enough. Or if you see separation vector, but it's 10-20 degrees, that's not necessarily a problem. And so in this case, just not necessarily an outbreak, but we did have a low-level jet intensification. So here by 0-1Z, you can see we were already pushing 250 to 300. And then of course by 3Z, we were in the 400 to 500 range. So yep, we can definitely check off that box. Now another area that I'm going to talk about briefly and give you just a quick introduction here before we go too far is what's called the Storm-Relative Velocity Enhancement. And this is a feature that John Stopcotti, my partner in crime up at North Platte, he's the SU up there, first kind of coined this phrase for this feature. And what we're seeing really is an airstream. But in this case, this feature may be inbound or outbound depending on your radar viewing angle, and you may not even be able to see it if it's perpendicular to the beam. But this is an asymmetric signature here that originates from the forward flank. And so what we're actually seeing is not a circulation per se. We're actually seeing an airstream emanating out of that. It's a descending airstream. And so when we look at research to see if there's some background to this, we do find that. Of course, this area that it's emanating out of, we know that's adjacent to the horizontal buoyancy gradient. And of course, this produces an area of bare clinically generated vorticity. So there's a lot of things going on here that suggest this is a region of, or a source region of vorticity in the near surface layer. What we can tell though, and we're using a simulation here by Lee Orff, there's kind of two areas you see, and this gets confusing for some. So for in this area that divides the green from the kind of the bluish purple, that's right along the forward flank downdraft. That is an ascending airstream that's been coined as the streamwise vorticity current, and you can tell it feeds into the low-level meso. I would say streamwise, sometimes not necessarily the correct term, but that's what we're assessing essentially with the ZD arc. In counter to that, what we're talking here is that airstream that's emanating from deeper into the forward flank where there's more colder, or actually it's colder, more negatively buoyant air, but you can see it's feeding directly into the region that becomes a tornado. So this airstream, this survey, is coming down out of the forward flank and then feeding underneath the low-level meso where it can be tilted and stretched. So, and we see other papers that kind of highlight this. We got a paper from Dahl et al. From 2014. You can see this trajectory here coming from the ambient air. The minute it hits the forward flank reflectivity gradient, it starts to obtain bare clinic vorticity, albeit crosswise in nature. But that as that airstream descends, in tornadic cases, this airstream makes a kind of a last second turn underneath the low-level meso. And that's important, as you can kind of make out from Parker and Dahl, that there becomes this conversion to streamwise vorticity through what's called the river bend effect. So this seems to be a critical feature that is somewhat separate from the mesocyclone itself. The meso plays a part in using the vorticity from this, but this is not just one big massive tube extending from 500 millibars to the ground. We've got the source of near surface vorticity, which supports a lot of the recent research showing this tornadogenesis that starts at the ground and builds up, not a descending dynamic pipe effect. With all that stated, we obviously can't see these nice, vorticity streams coming in off the radar. We have to utilize what we see with the 88D. And so we have to take a closer look at this Storm-Relative Velocity Enhancement, or SURVE region, in relation to the products we have. And so we go back to, a plan view of the conceptual model to kind of reiterate the portions we need to investigate, because this is going to help you as a warning decision mat. So while we know conceptually we've got the reflectivity, we can kind of tell where the forward flank is. We know there's also this airstream emanating out of that region. And I will add, this airstream is not only seen with tornadic supercells. I'll get to that in a second, but it's that turning process that's important for tornadic supercells versus non-tornadic. And so when we look at this airstream coming out of that forward flank, we have to kind of note some of the features about it, let alone just the existence of it. And so one of the critical things that we look for is that turning, and I kind of highlighted, so that descending airstream's coming in and it approaches that last bit of descending and maybe even a little bit of ascending under the level meso. We want to see signs that that airstream's turning. And maybe in this case, it's kind of hints that there's a convergence or there's a zero eye stop. Either way, we can tell something's happening with that airstream where it's turning. And that's important for us to find. So this might be a tool where we can actually start to evaluate something besides just low-level mesocyclone intensity, keeping in mind that obviously this is a feature you're going to see mostly in the lowest kilometer. So there is a range from the radar where you're not going to be able to see this. But the key thing is that turning equals getting underneath the meso, where due to vertical pressure perturbations, you're going to get that vorticity tilt and stretch to produce what could become the tornado. And again, this is fairly common in tornadic supercells, but also in this case, this is a non-tornadic event. Notice there's this airstream coming towards the 88D in this case in a relative sense. But in this setup, while I'm not showing you the placement of the low-level mesocyclone, what you can see if you were to have noticed the mesocyclone position, this is not making a turn in this case underneath the low-level meso. It's blowing right past that. While I don't have this shown, the ZD arc that was evident in the storm was highly disrupted with what was wet melting hail. Well, that added enough negative buoyancy to cause a pretty large momentum surge to where that airstream could not make that turn underneath the low-level meso. So in this case, you can kind of confirm this with the fine line as well, but that arc disruption alone, along with where you get the placement of this boundary, tells us that all-important conversion to streamwise vorticity likely did not occur, and so the vertical vorticity remains near zero. And so this is kind of a cutting-edge area that John and I are looking at, even beyond the TWIP, just to see the relevance that this has and if this feature can be utilized to help with tornadogenesis decision-making. So that's your kind of quick summary there of how the survey works. So now we're going to look back at this case itself. And it's important because the legacy reflectivity and velocity couplet features were basically unimpressive until well after tornadogenesis, with the vortex actually existing just outside of a new TOR warning. And that's what we're going to look at to see if there was some evidence that would have helped us with warning placement. And so we're going to look at these concepts introduced by the CR TWIP and just overall deeper radar analysis than half-degree ZSRM, to see if there were signals beforehand. So we're going to start about 20 minutes prior to tornadogenesis, and we're roughly 20 to 30 nautical miles south-southwest of the KDDC 88D. So we're close enough, we'll be able to sample that lowest kilometer pretty well. So we're going to start off here, T-minus 19 minutes to tornadogenesis. So in 0118 here, you kind of see two things here from even a reflectivity presentation. By the way, all of this is half-degree at this point. But the upper left is reflectivity, upper right is SRM, lower left ZDR, and the lower right's KDP. But you can kind of make out maybe a sign of, looks like maybe a remnant supercell there near Fowler, maybe starting to get occluded with maybe a merger. So maybe your attention's drawn maybe back towards the southwest. You say, well, maybe this is the onset of there's a new meso that's formed farther southwest near Meade. So, okay, fine, maybe that's a hook, maybe it's not. But so even if your attention is drawn into this area, the one thing you notice, there's no half-degree couplet. Maybe you think this thing's south of Meade as a couplet, but pretty low reflectivity. So the signal to noise ratio issue probably says that's not legitimate. You got to really question whether that's real. But, you know, if you had gotten previous reports and think, well, here it goes, if you're looking just at these two basic, you know, the top left and right panels, maybe that's why the warning went where it did. However, what that's conveniently omitting is we can actually utilize our velocity to notice there's a downdraft boundary well east of this area. So even if that is a circulation, which I highly doubt, it's likely sitting over more colder, stable air where, you know, tornadogenesis would be inhibited anyway. So that alone would say, okay, I don't need a warning, tornado warning in that area. I better look farther east. Now, I'll mention this downdraft boundary a little bit more here in a second, but notice there's a divergence signal south of the town of Fowler. It kind of indicates maybe a new downdraft or new forward flank. But anyway, so at this point for that area near Meade, or even the area near Fowler, this looks an awful lot like the Markowski and Richardson 2014 paper of the non-tornadic, the strong heat sink, where yes, you have a decent circulation, but the Louisville vorticity is displaced and it's sitting over this more stable layer where genesis is inhibited. Now, we could stop there and say, well, no reason to issue a tornado warning, but obviously we know a tornado occurred. So that's a sign that we needed to look at additional information. So let's take a look. First, we could say, well, is this area essentially from Meade towards Fowler, is that a ZDR arc? Well, some of that probably is. The other portion you do have to question, because as you can remember here, you know, we'd have that downdraft boundary. But if we use the whole thing, and even though I said you don't necessarily have to calculate the separation vector angle, this area of raised KDP north, which appears connected to kind of the older updraft and probably likely dying off updraft, you combine that with this broad region, it's probably more of a ZDR shield than an arc at this point. We do have a pretty good angle here. So, you know, even if you didn't have as high of a Louisville SRH in the broader ambient environment, this looks pretty good. But again, the problem with this is a good portion of that broader ZDR shield is sitting behind this colder air. So that's probably not a forward flank. There's probably not active size sorting for most of that raised ZDR. However, your attention should be drawn to this area south of Fowler. You can see that the brighter green, darker colors, much higher ZDR confined in that same area where we can kind of make out this divergent signal in that downdraft boundary. In other words, could this be the new forward flank? What's important about that too is we notice very low KDP and very low reflectivity. So that kind of hints that we only have a few sparsely populated large drops that are not going to produce a ton of negative buoyancy. And we've seen that through research really even since Vortex 1. That's critical for keeping that downdraft buoyancy only on the slightly negatively buoyant side. That's important for tornadogenesis. But we'll come back to that in a second. But nonetheless, we see this non-disrupted area that's in this area divergence. But we probably need a little more evidence that this is actually a forward flank. So let's first kind of say, well, if it is, do we have any sign of a Louisville meso that's not clear back over the cold air? So we're going to bump up using the 1.3 tilt into the 5,000 to 6,000 foot range. So in that 1 to 2 kilometer. Well, we do have hint of a circulation, and there's a little even sign of a little bit higher reflectivity in that area. So is that the greatest sign for Louisville meso? No, but it does appear we have some hint of a Louisville mesocyclone either forming, or even if it's disorganized, it's in that general area. And most importantly, instead of being buried clear back behind this downdraft boundary, you can see it's tracking right along that boundary, which matches a lot of the Markowski and Richardson research. So we do have a positive sign here that if that ZDR arc we could see south of Fowler is legit, and that's feeding streamwise vorticity into this meso, you know, things may start to change pretty quick. But at the end of the day, we still need to confirm that this is all connected to a new updraft. So we're going to bounce all the way up in the mid-levels of the storm here, up to 15,000, 16,000 feet. And we do notice various circulations. We see the one, as I mentioned before, north of Fowler. But it's really this other circulation that kind of piqued people's curiosity back here north of Meade. So no doubt there's a mid-level mesocyclone. We can see a ZDR column. So yeah, definitely no doubt that has potential to produce at least hail. But problem is at least for that circulation, we're way behind that boundary. On the other hand, while it's not quite as evident, we do see a mid-level circulation in that same area that we saw the low-level meso. So combine that with the fact there's a ZDR column and there's reduced CC, it tells us definitely have some mixed hydrometeors going on there to where pretty confident there's an updraft in that area. So that's checking a lot of boxes at this point, that something's going on here and there's increased probability of tornadogenesis in the following maybe 10, 15 minutes. But if you're not convinced from the previous scans, let's go back down, look at the half-degree data. Again, we continue to see our downdraft boundary, continue to see that kind of divergent signal in the velocity, indicating more than likely this is a forward flank. We still see that ZDR arc in that region. It's not disrupted. The other thing that's important, and we'll come back to what I mentioned with the survey, we should, since we're close enough now and we have a good viewing angle, we should see that air flowing out of the forward flank and moving towards that low-level meso to where it's turning. And sure enough, that's exactly what we see. We see this airstream moving, and then you can see a drop in the velocity data indicating some, or at least hinting at some level of turning that could say we're getting that all-important conversion to streamwise vorticity. And that's seen within ORF simulations as well. So when you put all this together, we're looking a lot more towards the Markowski and Richardson tornadic phase, where a little bit less of a heat sink issue, things are lined up. So at this point, this has countered a lot of people because there's no magical half-degree VROT high value and couplet at this point. But this is where we would need to put a tornado warning. No hook, no major couplet, but this is where the science says we need a tornado warning. So if you're not convinced, we'll keep jumping ahead, but keep in mind, at that point, we were able to stay ahead of the 13-minute lead time Gipper goal. Now we're inside of that. So you got to keep in mind that if the science says you can get that, but you're hesitating, then maybe you need to do a little more practice with this stuff because the signals were pretty good that there was going to be something ongoing in this area. But we're at T-minus 11 minutes. So let's check off some things. We continue to see our downdraft boundary in that location. We continue to see this area flowing out of that forward flank downdraft. The arc's becoming even more evident in that region. Notice still fairly low reflectivity in KDP, so it's just a few sparsely populated drops, but that gives us strong indication that active size sorting is going on to where we're getting that ascending SVC feeding into the meso. So, but we can see that again, a hint of turning there east of Meade, and that's exactly where our little meso up there at almost 5,000 feet is sitting. So again, if you weren't convinced before, all the signs are still pointing towards increased probability of tornadogenesis in this region. And again, that little meso is tracking right along the boundary. So if still not convinced, we'll jump all the way to T-4. For all intents and purposes, by the time you get this data, evaluate it, get into Warringen, get the warning out, and our partners get it, the tornado is probably ongoing. So we're kind of, at this point, we've probably spent too much time not believing what was there versus the data saying, hey, this is going to occur. But anyway, so we do have our downdraft boundary here. Kind of harder to detect exactly where we may have a turning of the flow, kind of two different areas. So I highlighted both, but still non-disrupted ZDR arc. So we can tell that the low meso should be, or at least should be continuing to become more organized and intensify. When we look up, not much there for the low meso at this point, but you're still seeing the lineup of not only the turning, but that this is tracking on the boundary. Because in many cases, you're not going to get a great couplet ahead of time. Using VROT, for example, is a great tool for message refinement once you have an ongoing tornado. But for tornadogenesis, it struggles in many cases, and this is a classic example where it struggles. So finally, tornado time. Still half-degree. We don't have any great couplet, by the way, but we continue to see the arc. It's not disrupted. We continue to see this airstream coming out of the forward flank. It's turning in this area where exactly the low meso is. And that's 2 minutes into tornadogenesis. Even the signs of the low meso up there at 4,000 feet is not the greatest, but we're not going to be able to adequately sample everything with the 88D, even at just 20 to 30 nautical miles. It's not a Dow. So we have to understand the limitations that we deal with sampling, that these features are ongoing, but the 88D may not resolve it adequately. So, just keep that in mind. So we'll jump ahead though, which I forgot to mention here, everything's still lined up along that boundary. So we'll jump ahead near almost 20 minutes. So at this point, the tornado has now moved just to the northeast of Mineola, a little bit, kind of a hint there of maybe a broader tornado cyclone, but still nothing to point at. But meanwhile, we can still see where that boundary is, and especially we can see the ZDR arc, and we can also see where this airstream is coming in and turning. I don't highlight the little meso, but it's still obviously turning underneath that circulation. T plus 31 minutes now. Obviously, and I bumped up to the 0.9, which is a good reminder for everybody that it's a good reason to use the Merle instead of sails for stuff that approaches. It's not just a tool for using in QLCS. It's great for supercells that get within 20, 30 nautical miles as well. But anyway, using the 0.9 slice, we still make out, that downdraft boundary. We can still kind of see a broader ZDR, but it's not disrupted. And that airstream's continuing to turn. So that was that tornado in that phase of the supercell. Move on to the next one just to see, and this one was a little bit weaker, EF2, but on the ground, similar amount of time, we can see the same features. We see the ZDR, it's not disrupted. We can see the survey airstream, we can see it's turning. So those features are there repeatedly in the storm. We jump out to the next one. Now we're out about 45 nautical miles. We're high enough, we can no longer directly sample that Storm-Relative Velocity Enhancement feature, or that airstream. So keep in mind, there is a range from the RDA where you're gonna have to use other tools. So what we're seeing here, again, is not the survey, that's more the low-level mesocyclone. However, we can still infer some things that do impact the survey. In this case, we see there's this ZDR arc along the forward flank. We don't see any disruptions. In other words, there's no low ZDR cutting across it. That gives us pretty decent confidence that while we don't know if the airstream's turning under that meso, at least from a buoyancy aspect, it doesn't have a ton of negative buoyancy where the desire would be to have a momentum surge past it. So that at least gives us, in a probability sense, that maybe there's increased probability still that things are lining up. The other thing I will mention though, instead of the survey, is the SVC. And that's that ascending airstream feeding into the meso. Notice how the ZD arc, we can kind of see this stronger inbound values line up perfectly. That's a reminder that the ZD arc is giving you a hint of what's going on with that airstream. That's why it's such a powerful tool for low-level meso intensity. So we'll jump ahead to the last tornado. Now we're out at 65 nautical miles. To be honest, there's nothing you're sampling that's low level at this range. Everything is mid-level in nature. You're up above 2 kilometers. So unfortunately, even though this tornado occurred, there's not much you can really assess in the low level. So you're having to revert back to kind of your older, okay, is there a supercell? Am I getting spotter reports? You do the best you can. And I just wanted to explain that this isn't a bulletproof set of tools. There's going to be limitations with range from radar. Well, I'd love to be able to say we're going to get extra radars that keep, the range from the storm no more than 60 nautical miles. That's probably not going to happen. So just a reminder there. And of course, can't really evaluate the arc much. And of course, the storm moved and became multicellular. So let's kind of review with what we've looked at here and the storm features and implied processes that were ongoing in that roughly 20-minute period. So these tornadogenesis signals existed in both dual pole and the non-half degree storm-relative velocity couplet analysis, south-southeast of Fowler. That's what we're talking about, especially the downdraft boundary. So despite that more textbook kind of reflectivity presentation near north of Fowler and near Meade, those older mesocyclones were undercut by colder, more negatively buoyant air. And so we should alone, since really downdraft boundary analysis is not anything new, using that should be second nature, but it was obviously omitted for reasons that I can't explain, but we're not alone in that. I see that frequently across the agency. So these are simple tools that we should be using, not just looking for couplets. I saw even a storm last week that you could see a major outflow boundary surging well south of a storm, see the fine line, everything, and yet a particular office put out a tornado warning. I'm surprised they never got any verification. So we need to keep these things in mind. The science has been established for years on this. We just need to use it. So in contrast, a new level meso and downdraft in new forward flank was altering that level flow to favor tornadogenesis, despite getting the unimpressive reflectivity and even the couplet analysis. So existence of a non-disrupted ZD but with minimal reflectivity in KDP, as I suggested earlier, tells us that one, there's active size sorting along the forward flank. Again, that's going to increase the storm scale SRH when combined with the high ambient SRH, supports intensification and better organization of that new level meso. So even though it looked somewhat marginal within the velocity presentation, that should give us high confidence that things are going to change. In addition, again, that downdraft boundary in the new forward flank was composed of only a few large drops, which tells us that that negative buoyancy is minimized, as seen in numerous tornadic case studies over the last 15 or so years. Again, velocity product analysis indicates two extremely important items that build on the non-disrupted arc. One, that new level meso was seen tracking along or immediately on the cool side of the downdraft boundary, similar to the Markowski and Richardson conceptual model for tornadic cases. But more importantly, that survey, that storm-relative velocity enhancement on the cool side of the downdraft boundary, displays turning and or convergence underneath the level meso for nearly 15 minutes prior to genesis. And that's similar to high resolution simulations of other tornado cases. So you put this together, there's a strong indication of near surface baroclinically generated vorticity being fed directly under the level meso, where it can be abruptly tilted and stretched into a tornado. So a question for everybody to ponder, and it's just, I've left this kind of out there for the other times I've presented. So it's 2020, now albeit this case was 2019. And this is far from being the lone example of this. Why are we seeing NABS warning mats still using 1970s era warning decision tools, despite mounds of research and training material providing for more advanced interrogation methods? And, you know, especially being in the TWIP, but aside from that, you have to reassess after training's out there to see if people are using it. What are the blocks to people applying this? And what I've kind of found out is that I think for some individuals right now, it's simply too much information to process at this stage. And I'm pretty sure that's likely from insufficient experience and skill in assessing these features. But practice, and this is where there's hope on the horizon with Cobras, and on a team that's looking at multi-office use of Cobras for training. This is where we will gain that skill set. For those that are passionate about radar interrogation, I'm pretty sure that we can actually solve this first bullet. But you got to be passionate about it, because this is going to require a lot of training, even in the cool season, where you're looking at cases maybe several times a month, going through displace real time, whether it's July or January. You build expertise and cultivate that by practicing and making sure your skill set doesn't decline. Because ultimately, if you just go through these modules and then walk away from it, you know, most folks' tendency is going to be to go back to what they've always done if they're not comfortable with it. So we need to practice. We need to use things like Cobras. The other thing, though, and being truthful here, for others, there's a desire, I think, for radar interrogation to be easy in order to focus on other activities they may be more passionate about, DSS, social media, maybe even mesoanalysis. And so the old saying of trying to fit a square peg into a round hole leads to mediocre results is very true in this case. You know, if your passion is elsewhere, that's okay. I don't want to try to force people into something that they're not passionate about. On the other hand, we need those that are passionate to become essentially the Top Gun warning meteorologists. And forgive the cheesy graphic here, but we need those subject matter experts to specialize essentially as the heart surgeon of warning mats. In other words, they're the ones that are doing the first bullet there. They're fixing, you know, their inexperience, so that they're not just trying to be the jack of all trades primary care doctor. And that's, I know it's hard for some people to hear, but if your passion isn't into doing this routinely, then maybe it's best to let those help guide you. So if you are on the radar desk, let the subject matter experts help guide you. Or if you're just uncomfortable, let those that have done this be the ones that make those decisions for you. It's not a slam upon your skill set, but if your passion is elsewhere, knowing how complex, and it's only going to get, you know, the fire hose of information is only going to get more extreme, you've got to be able to be the one that puts in the time and energy. Otherwise, we will stagnate on improvement. And so that's kind of my last phrase for everybody to ponder. Otherwise, I do appreciate your time, and guess if there's time for questions, I can take a few.